Okay, on this video we are going to talk about the same problem, constant coefficients, differential equations equal to 0, homogeneous, second order. But what happens when we have repeated roots? And there we will have a big problem. Okay, now let's solve this. Usually we write here, down below the characteristic equation is going to be m squared minus 2m plus 1 equals 0. There is no need to use the chicharronera formula because this is very clear. Two numbers in which the multiplication is 1 and the addition is minus 2. So n minus 1 and n minus 1. So what happens here is that you have repeated roots. My first root, m1 is equal to 1, and my second root is equal to 1. So what happens is that m1 is equal to m2. So what is the problem here? If I try to write the general solution, the homogeneous solution is going to be c1 exponential of x, where the m is equal to 1, plus c2 exponential of x. So engineers, I don't have two solutions, because if I factorize the exponential of x, what I have is c1 plus c2 exponential of x. And a constant plus a constant is still a constant exponential of x. So in the end, we have only one solution. We have one solution. But in reality, because this is second order differential equation, we have to find the second solution. Okay? So where is my second solution? y2 equal to where is it? Okay? It should be there because it is second order differential equation. We should get two solutions and two linear independent solutions. And by the way, let's try with the Wronskian of these solutions. The Wronskian of exponential of x, my first solution, and the exponential of x, my second solution, is very clear. It's going to be 0. But let's do the test just for the sake of learning. Exponential of x and exponential of x, the two solutions. Exponential of x and exponential of x, the derivative of this. So this is going to be exponential of 2x minus exponential of 2x, and this is clear, equal to 0. So they are linear dependent solutions. So in the end, we have the same solution. We don't have linear independent solutions. Okay, now, how to find the second solution? Okay, so what we have to do, we have to develop a method that is called order reduction to find the second solution when we know the first solution. Okay, so I'm going to erase this part. Just let's keep this problem and let's develop a method to find the second solution. Okay, now the method is called order reduction method to find second solution. Okay, now let's assume this. Assume that we have this differential equation. Assume that you have second derivative plus p of x, first derivative plus r of x, y equal to 0. Okay? Now the coefficients are variable. Okay, so that means that this method works for constant coefficients or variable coefficients. Okay, now let's assume another assumption that the first solution y1 is known. That we know what is the first solution. How do we get the first solution? We don't care how we get it. What we care is that we know the first solution. Now, if this is solution, then if you replace it in the differential equation, then if you take the first derivative and the second derivative and you plug in or replace it in the differential equation, then the y1 second derivative plus p of x first derivative of the first solution plus r of x the first solution, it is identically equal to 0. So there is no question, it is equal to 0 because y1 is a solution. Okay? Okay, so this is true. This is true. Don't question this. This is true because it is solution. Okay, now the proposed second solution is going to be something like this. The second solution, it is proposed like this. My second solution equal to w of x times my first solution. Now you may say, hey, this means that the second solution is linear dependent of the first solution. Well, that will be true if this is a constant, but it's not a constant. It's a function of x, right? So the question is, what is w of x? So that this is solution. Okay. Okay. So if this is a solution, then if we replace it in the differential equation, it should be equal to 0. So let's do it. But in order to replace it or plug in this differential equation, we have to find the first derivative and the second derivative. So let's do it. So y2 first derivative, y2 first derivative is going to be the derivative of this, derivative with respect to x of w of x times y1. So because we have a multiplication there, then it's going to be w of x y1 prime plus w prime of x y1. So it's this times the derivative of this plus the second one y1 derivative of this, which is here. And this is the second solution, first derivative. Okay, now as you can see here, we are developing a theorem. Okay, and you don't have to do this every time. What we are going to do in the end, somewhere here, we are going to get a formula to find the second solution. Okay, so now we need the first derivative is there. Now we need the second derivative. The second derivative is equal to derivative of this. So it's going to be the derivative of respect to x of w of x y1 prime plus derivative with respect to x of w of prime of x y1. Now because you have a multiplication there, you have to develop each one of them. Okay, so what you get here is w of x y1 double prime plus w prime of x y1 prime. So very careful here is this times derivative of this, because it already has a derivative, then it becomes second derivative, plus this y1 prime derivative of w of x w prime of x. Okay, now this is just the derivative of this, now plus derivative of this, because this already has a first derivative, is going to be w prime of x y1 prime. Okay, and then plus this derivative of this plus y1 derivative of this, because it already has a derivative, then it becomes second derivative of x y1. Okay, now let's replace in the differential equation. So is this number plus p of x, this number plus r of x, this number y2, or it's actually function. Okay, let's replace in the differential equation. So the first one, w of x y1 double prime plus w prime of x y1 prime plus w prime of x y1 prime. Actually, because this and this, they are the same, we can do 2 times this number, but let's leave it like that, plus w double prime of x y1, so that is the second derivative. We are here now, plus p of x, my first derivative. My first derivative is this of the second solution. By the way, this is y2 double prime. P of x times w of x y1 prime plus w prime of x y1, and then plus, so we are here, w prime plus r of x, y, and the y is equal to, the proposed solution is w of x, y1. And this is supposed to be equal to 0 now. Don't forget what we are looking for. So what is exactly what we are looking for? Because the first solution is known, so we don't have to find the first solution. We propose the second solution as w of x times my first solution. So what we are looking for is w of x. This is exactly what we are looking for. So the unknown is w of x. Now, p of x is given and r of x is given in the differential equation. Okay, now let's factorize what we can factorize. So let me see here. I see w of x here, I see w of x here, and I see w of x here. Let's do the factorization. Okay, w of x times, sorry, this doesn't look very much. Okay, so I'm going to factorize w of x times my first solution, second derivative here. If we factorize it from here, it's going to be plus p of x y1 prime, because remember this p of x times this and times this, and then plus r of x y1, and that's it. And then the rest, plus, I'm going to do these 2 times, maybe if we can factorize anything from there, okay. Now, 2 times w prime of x y1 prime, this is 2 times, plus w prime of x, sorry, second derivative of x y1, and then this part, which is plus p of x w prime of x y1, and this is supposed to be equal to 0. Now this is actually here. Now here's some magic. Well, it's not magic. This is equal to 0. Y is equal to 0. Remember this part. y1, the first solution, second derivative, plus p of x, the first solution, derivative, plus r of x, the first solution. This happens to be 0 because it is actually the first solution. Replace it here, so that is to be true. Okay, so the only thing that survives is this part. Okay, now can we factorize something from there? Okay, yeah, as a matter of fact, yes. I'm going to pass this and this to the other side, and I'm going to factorize w prime of x. Okay, so what you get here is w prime of x y1 prime. No, yes, sorry, we are here. Okay, the other to the other side, but negative, minus, and let's factorize the w prime of x. So it's going to be 2y1 prime plus 2y1 prime, and then plus p of x y1, and then w prime of x here. Let's check. So we have this number here, okay, and this times this is here, okay, and that to the other side. Now here comes the order reduction name. Why it has this name? What we are going to do is to reduce the order of this differential equation. Now this differential equation is second order because here you have second derivative. So what we are going to do is this. I'm going to do mu of x equal to w prime of x. Therefore, mu prime of x is equal to the second derivative of w of x. Okay, so how does that help? Okay, so what helps here is that instead of writing second derivative here, I'm going to write first derivative, mu prime of x y1 equal to minus 2y1 prime plus p of x, the first solution, and here mu of x. Okay, so what we are going to do is this y1 to pass it as a division, and this mu of x, I'm going to pass it as a division here. Okay, so it's going to be on this side is going to be mu prime of x. It is actually the derivative of mu of x respect to x, and then divided by mu of x. Okay, equal to minus 2 y prime y1 prime divided by y1. This is going to divide here, but also it's going to divide here, so it's going to be plus p of x. Okay, maybe we should only write okay, let's leave it like that. And the differential of x, we can pass it to the other side, so I'm going to skip that step because I am running out of the space. So differential of mu of x, and then the differential of x here. Okay, now the y1 was cancelled here. Okay, this mu of x is as a division, and here is what is here. Okay, so what you can see here, this is a variable separable differential equation that we have solved before. So I'm going to take the integrals on this side and the integral on this side. Don't forget the minus here. Okay, so this is very easy. This integral is the natural login of the mu of x. And this is equal to, now pay attention to this, minus is going to be 2 integral of y1 prime over y1 differential of x plus integral of p of x differential of x. We can solve this because this is natural login again. So it's going to be the natural login of the mu of x equal to minus 2 the natural login of y1 minus the integral of p of x differential of x. We cannot solve this integral because we don't know what is p of x. Now let's take the exponentials on both sides. Okay, so this and this cancels. So what you get here is mu of x is equal to, this minus 2 goes in the power, so it's going to be the exponential of the natural login of y1 squared minus, because it is minus, and then minus integral of p of x differential of x. Okay, so the mu of x is equal to this and this cancels, y1 squared, y1 minus 2, and then exponential of the minus integral of p of x differential of x. But remember that mu of x is actually y prime of x, and what we are looking for, we are looking for the w of x. Okay, so to find w of x, what we have to do is to take the integral. So w of x is going to be the integral of this integral of the exponential of the minus integral of p of x differential of x. Now this y1 to the power minus 2, I'm going to write it below exponential, no sorry, y1 squared and then differential of x. Okay, engineers, so what we have found is, here is the formula to find the w of x. Okay, so to find the second solution, all you have to do is, the second solution is w of x, apply this formula with the first solution given and then p of x given, replace it here, calculate the integrals. You have two integrals, one here and the other big one here. And once you calculate the w of x, then you multiply that times your first solution and you get the second solution. Alright, now this is called the order reduction formula. Okay, now let's do one example on the next video.